This is James speaking from JTAG Technologies in our UK office. Welcome to today's webinar, which is an introduction to boundary scan, or if you prefer, boundary scan essentials. The aim of today is to try and give you some background into the technology of JTAG boundary scan and give you an insight in what you can achieve. So I think we're just about clicked over to 9:30 Greenwich Mean Time. I think we're still on Greenwich Mean Time. 10:30 European Time, and whatever other times there are around the world. So let's make a start. Today's agenda, as I say, we're going to look at a little bit of background, why boundary scan was developed and introduced in the first place. Then look at how it works at a device level. A little look at the registers and the technology involved there. Then we'll move on to what you can achieve with boundary scan, what the possibilities are and the capabilities are at a board level. And then we'll briefly take a look at a little utility you can download. It's something we made to try and get people introduced to the way it works. And also available. I can't remember what that is, so that will be exciting for me to discover what those slides are. So let's move on. The background. Well, the technology was developed when people started to use more and more surface mount devices. So up until the early mid-80s, most PCBs were manufactured using through-hole components, ICs and resistors and passive components, all were through-hole. And wave flow soldering was quite reliable, and in-circuit testing was used to probe the pins of the through-hole components in order to test their functionality and also to test the connectivity between them. But as surface mount devices became more prevalent, more widely used, the bed of nails technique became more difficult to implement, and so some people sat down and worked out a method of embedding test logic into devices so that it could be used in place of the nails. So that was called the Joint European Test Action Group. But within a year, they dropped the E and it became the Joint Test Action Group, and we had some American involvement. And very quickly, actually, for a standard, they proposed the technology to the American organization, the IEEE Computer Standards Authority, and it was given a standard of IEEE 1149. Test access port and boundary scan architecture, but the name stuck. So the JTAG name kind of stuck with the to the standard name, and boundary scan and JTAG were used interchangeably as terms to describe this technology. Although since then JTAG has been, or the interface has been used for other purposes, and now you see JTAG being referred to as a debugger port, for example. But we'll come on to that a bit more later. Now, in addition to the base standard that was developed as long ago as 1990, there have been some updates to that standard, and there have been some additional standards. So, for example, extension 1149.4 was an attempt to address analog testing, because the base standard is focused on digital. Then we have an in-system configuration, an ISC standard 1532, which is a superset of 1149. Then we see some efforts to enable testing of AC coupled signals like low voltage differential signals and embedded test and so on. So the 1149.1 was the base, and from that base other standards have grown and emerged, some more successfully than others. So if you look at a picture here, you can see that the way the technology moved basically throughout the 80s and 90s, and from this through-hole technology I referenced earlier through to the surface mount devices that we see today. So that's your ball grid arrays and your QFPs and your TSOP packages, all things that were very tricky to probe using bed of nail systems or flying probe test systems even. So if we look at a cross section of a circuit board, please forgive the rudimentary nature of this diagram, but it illustrates a point, I think, that in traditional testing we had these nails, these orange orangey yellow symbols here. And with those nails, you could probe test pads or vias, and you could use that access to test interconnections between devices. But obviously, when circuit board design became more complex and more dense with more layers, you ended up with tracking systems like this with blind vias, so vias that don't come to the surface of the circuit board, so can't be probed, and thus you need another method to access those pins or balls and test the continuity between them. And so that was a perfect solution for boundary scan. And so because boundary scan is embedded in the silicon wafer of the chip here, you see the little orange block at the top, and using that test access, you could drive a signal through a bond wire, through the ball of the device, through the track, and then along and test for continuity. And obviously, if there's no continuity, we see a test failure. So really, that's the sort of one of the driving forces, was to improve accessibility on these types of boards. So how does it look at a device level? Well, let's take a look at a few slides to show that. So your standard device here has a number of pins accessing the outside world, input pins and output pins. But a boundary scan device has the addition of this test access port logic block, the TAP as we call it. And the TAP controller, which is part of the system, is a 16-stage state machine which manages the data flow around the logic within the devices, the test logic, that is, not the functional logic. Now, to control the test access port, you have a number of signals, and these are as follows: test data in, test data out, test mode select, test clock, and optionally a test logic reset line. So you may see test logic reset, you may not. There is another method of resetting the test logic, so it's not always evident on all boundary scan compliant parts. In terms of registers, we have a thing called the bypass register, which allows a device to be bypassed from boundary scan activity. We have an identity code register, which contains a 32-bit JTAG reference code, which includes manufacturer's information, device part number, device revision number, and so on. Then we have an instruction register, which is used to process the different modes of operation of the boundary scan device. And finally, we have what's known as the boundary scan register. And the boundary scan register is the main test logic that we use to interact with the outside world. So it's used to capture data on input pins, for example, or latch data onto output pins, whilst the normal functional core operation of the device is suspended. So when you're in boundary scan mode, the core is isolated, and the control of the pins is solely by the boundary scan register. Okay, so that's an important point you need to be aware of. Additionally to the standard registers, you might find there are private registers. In programmable logic devices, these could be programming registers for the fabric of the device. They could be BIST registers, built-in self-test registers that are used for running built-in self-test on the core logic. That will be in more sophisticated devices, ASICs and so on. So there is some flexibility built into the standard to accommodate device-specific requirements. Okay, now all of this, apart from the private registers and instructions, all of this information about the boundary scan logic in the device is described in a model called the BSDL model. That's Boundary Scan Description Language Model. That has its own standard, by the way, IEEE Standard 1149.1b. And if the vendor of a device claims that their device is compliant to the standard, the base standard 1149.1, then they must supply the BSDL model. It's part of the compliance statement. So, and it's an important bit of information because it's what is used by nearly all test software systems in order to manipulate the part and use it for testing. So let's move on. What are the test possibilities with JTAG boundary scan? Well, the first thing we want to do is test for the functionality of the boundary scan itself. So we see here a circuit board depiction with two boundary scan compliant devices on it, an FPGA and a microcontroller in this case. And we see here shown the test data in and the test data out signals. And they're currently shown going around the boundary register, out of the FPGA, back into the microcontroller, back out, and so on. And one of the fundamental things that we want to test first of all is the continuity of this line and also the continuity of the control signals. That's the test clock and the test mode select. They're not shown here, but imagine they are in the picture. And so we do what's called an infrastructure test. And the infrastructure test does a number of things. It captures the default contents of the instruction register, this thing called capture value. It captures the identity code register if the device has one, and then it tests for the continuity of the TRST line if it has that as well. Optionally, you can also check that the boundary scan register length, the number of bits in the boundary scan shift register, are the same as defined in the BSDL model. Now, I should have mentioned that earlier, that the boundary scan register is in fact a shift register. And so it works on a serial in. You shift a pattern in serially, and then you latch it out parallel. But that will become apparent, I think. So one of the tests that we want to do using this shift register would be what we call the interconnections test. And so in this example here, we might be loading a bit pattern into the FPGA in order to control the output pins, latch that pattern onto the interconnects, and then capture that pattern on the inputs of the microcontroller. And in doing so, we can also test connectivity through series devices, serial resistors, and also active things like buffers, as we see here, as long as we have control of the controls of the buffer, the output enable, the chip select, and so on. So straight away, you can see that there's quite a lot of possibilities here for testing continuity between parts and through transparent devices. And the tests we perform will check for open circuits, short circuits, stuck at faults, stuck at 1, stuck at 0, which normally represents shorts to ground, shorts to VCC, or open pins. We can also use the boundary scan register to stimulate other parts. So for example, LEDs, we can light up your LEDs. We can test for switch closure. We can test connections up to connector points, up to external interfaces. And we do that, by the way, by deploying further boundary scan elements in an external module. So if you imagine you've got an FPGA type device deployed in a module, we call it a digital I/O module, then you can extend the boundary scan chain, so through the FPGA, through the microcontroller, out, back through, and then into the digital I/O module, which is containing more boundary scan devices. You can fool the system into thinking that the connector here is a boundary scan element, and thus you can test that continuity as well. Most cases actually we use a separate test access port, but you can serially link the devices on the board with the devices off the board if you choose. Resistor presence of pull-ups and pull-downs, of course. If you can access the net that they're connected to, you can drive that net to the opposite value. So in the case of a pull-up resistor, you would drive the net to 0, and then you would tri-state the driver, turn the driver off, in other words, and monitor that the pull-up has pulled the net back to the correct value, or the pull-down. Some special devices like memories, we can create tests which allow you to write to the memory, read back from the memory, and using a selected number of test patterns, so we don't have to write to every memory location, we can detect any shorts or opens on the address and data and control signals. So we just use a small number of carefully selected patterns to do that, and that means we can test quite large memory devices, dynamic memories, DDR memories, DDR3, DDR4 even, in fact. So quite a lot of scope there for testing that type of part. LVDS I mentioned earlier, so there is this special extension to the standard called 1149.6, which has an extra instruction. So as well as an instruction called xtest, which is the external test instruction that controls the boundary scan register, there's an instruction called AC xtest. And AC xtest allows you to generate either a fast pulse or a fast pulse train in order to bridge the decoupling component, normally a capacitor. And there is a detection circuit on the receiver end of a .6 compliant part, which can detect the that pulse or pulse train. Additionally, we can be quite clever in how we use the boundary scan register access, and we can mimic the buses like I2C and an SPI, and we can use it to test and program I2C devices and SPI devices. So we can program SPI flashes, we could set up real-time clocks over I2C, or we can read value from I2C temperature sensors, or things like that. So some sort of functional testing in a way. And additionally, there are modules available in the market that allow you to monitor analog signals via boundary scan. So specific modules that have been built to take analog measurements, frequency measurements, and that kind of thing. And that obviously increases the scope of the test capability as well. So we keep going. I keep pressing the button and more things keep appearing. Oh yes, so a lot of those tests that I mentioned earlier, so from the infrastructure or the scan chain test, the interconnect test, the switches test, the connectors, and so on, a lot of these tests can be generated automatically using automatic test program generation tools. But as well as that, there is some possibility to write scripted tests in a system we call JTAG functional test that is based on Python. Not exclusively based on Python, because there's also the possibility to create these tests using LabVIEW or .NET framework programming options as well. But Python is well liked and well used, and it allows us to create tests which involve not just a sequence of test patterns, but conditional branches and loops, and the sort of techniques you would associate with functional testing. So if you have more complex logic elements that you wish to set up, I'm thinking of memory controllers, that kind of thing, or other devices with a lot of registers that need to be constantly loaded with a sequence of patterns. Then the JFT system, the JTAG functional test system, using Python is a good way to go. Finally, we have what we call our emulative test products. So right at the beginning, I mentioned that JTAG was originally devised to access the boundary scan logic, but as a lot of you may know, it's also an interface that's used by emulator tools to access the debug modes of microprocessors, for example. So looking specifically now at the right-hand block, the microcontroller block here, you'll find that there is a debug mode which comes as part of the embedded core of the device. And typically this will be something like an ARM core. In the olden days, be an ARM 7 or an ARM 9, but now we're looking at Cortex cores, Cortex A, Cortex M, that type of thing. And via the JTAG interface, we can set this up set the devices up into their debug mode, and we can use, well, and from the core, we can set up memory writes and memory reads in order to set up the embedded controllers and elements within the device. So for example, rather than using the boundary scan register to test a memory, we could set up the embedded memory controller, the block marked EMC here, via the processor core in order to perform a faster memory write action, a memory read action. So that would test it closer to its functional speed rather than the boundary scan register speed. Similarly, we could program embedded flash, or we can set up embedded analog to digital converters, and also digital to analog converters. So we can take analog measurements and create digital patterns and so on. So quite a lot of extra capability is offered by the system we call Core Commander, where we take control of the debug element of a device. The translator works in a similar way. If your device, if your FPGA has been designed, or the fabric of your FPGA has been laid out using an embedded interconnection system like Core Connect or Wishbone, or there are many others, and the names escape me at the moment, but if it is set up that way, we can provide a bridge between the boundary scan interface, the JTAG interface, and your embedded interconnect system, and again allow you to perform memory writes and memory reads to those IP blocks. So that's what we call Core Commander FPGA, but this is Core Commander processor over on the right hand side. So that's some added value over and above the original intention of the base boundary scan standard. The manufacturers at the bottom there illustrate some of the device cores that we support, from ARM and Analog Devices, Infineon, Microchip PICs, and so on. ARM being the most popular, of course. Okay, so moving on to the sample tool to download. So there's a website, JTAGLive.com. It's one of our products, so I'm make no apology about that, but it's there if you weren't aware of it. And you can download a system called Buzz, and that has some basic capability that allows you to access the boundary scan register and do a point-to-point connections test between two devices. You can run Buzz on existing hardware that you might have, controller hardware. So if you have an Altera Byte Blaster, I think they're called, USB Blaster, I think they're called, or if you have a Xilinx download cable, you can use that. Or we sell ourselves a fairly low-cost interface called the JTAGLive controller. It's about 195 euros, I think. So that can be used as well. And it allows you to auto-detect a scan chain, so you can connect up the interface to your board, and it will sniff out or detect what's in the chain first of all. So it will identify the manufacturers of the devices and how many devices you have in your chain. So when you connect it to our demonstration board, for example, it comes back and says, well, we've got an NXP device here and an Altera device here. Because it's managed to extract that manufacturer code from the ID register, but it doesn't know the precise device, so you still need to give it extra information. And so if you read the top of the device, you'll know that it's in the case of our demo board, it's an NXP LPC 2486 or whatever, and then you need to go and get the BSDL model for that part, assign it to this device in the chain, and then you'll find that you've got full information of the devices, and you can start performing meaningful tests like the infrastructure test. So after you've done your infrastructure test, you can move on to the Buzz mode, and the Buzz mode allows you to buzz a connection between 2 points. So in here it's 2 points actually on the same device, but illustrated on this example, but normally it would be a point from one device to another. And like we call it buzz because it emulates the buzz mode of a multimeter. So it affects you're using boundary scan to take a point-to-point connection test. And there's even a little noise you can turn on, so it even sounds like a multimeter. There's a sample mode. Now, I'm not sure if I mentioned all the operational modes. In fact, I may have skipped over that. But part of the boundary scan instruction set is one called sample, and that allows you to asynchronously sample an input pin while the device is normally operating. So I said right at the beginning, I think that during external test operations, the device core is isolated and not working. Well, there is a mode of operation where it's not isolated, and that's called the sample preload mode. And we use that so we can set the board running in its normal operational way, and then use the boundary scan register to asynchronously sample an input pin and look at its value. So that's what this watch feature of buzz does here. And so if you were to toggle this switch SW2 here, you'd be able to see the value toggle in the watch window. So simple as that, really. It allows you to look at see if a pin is either static or toggling high, toggling low. And we will be enhancing buzz actually soon to improve that capability to offer more pin monitoring. Testing multiple connections, so we can assign multiple connections to the measure window here, and you can test from one device to another, or you can drive values through a small active device. Could be an inverter or a buffer or something like that, and you can check that the value you drive is the same as the value you want to receive. So it's just a way of driving multiple pins at the same time using X-test again. And there are some constraints features where you can turn off or turn on other devices that might be causing contention during that test. Now, that would be something that was taken care of automatically with the higher end tools, but in the JTAGLive tool set, that's something you have to do yourself. Okay, so that really ends the introductory session. If you want to know some more about some of the tools that we have, so we mentioned JTAGLive there very briefly and looked at the JTAGLive buzz element. There are more recordings on how the tools work. I think the next one called Advanced or Next Stage Boundary Scan, I can't remember exactly what it's called, on our website, gives you some more indication of how JTAG Pro Vision, which is our high end or higher end automatic test program generator, works, and the capabilities that it has for generating tests, device programming capabilities, and so on. That's something I should have mentioned as well, of course, but device programming, but that's coming in the next webinar as well. So we've got a whole session on device programming using boundary scan, and after that we have a DFT seminar as well, webinar, which gives you some ideas on how you actually design in the boundary scan and the pitfalls to avoid. So I believe that's the end. Thank you very much for coming along today. This recording, or there's a similar recording already available on our website. I see I have a question. Okay, regarding BSDL models, but I can help you with that, Neil, later on. Thanks again for attending. Questions can be sent to info@jtag.com, and we will get back to you very quickly. Thanks again. See you again soon, I hope. Bye for now. Hello, everybody. Hello, thanks for sitting through the recording of that introduction to boundary scan. I'm here now to answer any questions you might have. I noticed we had one or two in the pop-up during the session, but happy to take on board anything else that not answered. Okay, so we do have one question already. Where do you get the boundary scan device models? That's a good question. Mostly they're available from the manufacturer's websites. So if you go to xilinx.com or altera.com or whomever you're looking for, you may often find a dedicated section where you can download the BSDL models. Sometimes you have to register, sometimes you don't. So please look there. We can supply models, so we do have build up quite a library of us on our own, but it's always best to go to the manufacturer to ensure you have the latest version of those. Okay, any more questions? Okay, I see one more question here about how fast does the clock run? Yes, well, that will depend on a couple of factors, really. The TCK rates of the devices themselves. So if you have a chain of devices, you can only run as fast as the slowest device in the scan chain. Typically, we're talking around 5, 10, 15 megahertz. Some systems can clock faster. I mean, our high-end systems can clock up to 40 megahertz, but only if the devices allow it and the design allows it, because of course you have to treat this clock like a clock, and if it's not terminated correctly on your board, you won't be able to clock at those high rates. So there's quite a few sort of factors involved, and more often than not, it's a trial and error situation. Okay, that's that question. Any more questions? I can't see any at the moment. Somebody's asking about other types of JTAG providers and what are the differences. Well, that's a good question. Depending on who the other supplier is, I can't really answer that. I mean, what I can say is that we offer a range of product from the JTAGLive system up to our ProVision system. So in terms of cost, we can offer quite powerful solutions using Python from around about £1,600 up to fully automated systems using automatic program generators, which are several £1,000s, tens of thousands actually, for the what we call the ProVision system. So we've got a product to suit all pockets. I think that's fair to say. The fact that we use Python as a scripting language means that you can develop quite a powerful solution using an off-the-shelf language rather than having to learn a more sort of a cryptic sort of language that might have been developed by the manufacturer. But yeah, I mean, contact us, send me an email about what your requirements are. I can figure out the optimum solution from JTAG Technologies. We can offer you an online demonstration, or we can come and visit if you need a face-to-face demonstration, and you can make a decision on that. I suppose that's the best way to do it. Compare and contrast in person. So one of the other aspects that people are quite keen to learn about these days is the thing we talked about at the end, the core commander, because it doesn't use the IEEE 1149 standard logic within the device, but allows us to leverage the core emulator functions of the part. And I touched on that briefly during the presentation, but it's quite a powerful thing, because what it allows you to do is access more elements of the chip. Often in mixed signal devices, where you've got digital and analog functions within a microcontroller, for example, the boundary scan only allows you to access the digital side, and at a speed that is governed by the boundary scan register length and the TCK frequency. So having the ability to go in and interrogate IP blocks within the device, activate analog portions, activate embedded controllers like for I2C or SPI or DDR memory controllers, that opens up a world of opportunity. It's not without its difficulties, I have to be honest, because it does mean you have to have a deeper look into the data sheet of the device to pull out the necessary registers you need to write to. But once you've established it, it is something you can reuse, and it is something that provides some higher power capability. What else have we got to talk about? Just a few minutes left on this session, I think. I mentioned Provision as well as, so we mentioned JTAGLive as an example, and we use that as an example because it's easily accessible. It's easy to get on our website and download the package and play with it. You can request additional evaluation licenses on the Python side of things, as well as the free buzz element. But as you move on, as your needs change, and if your designs are large designs that require more thorough testing using automatic tools, then the Provision system is something you might wish to look at. That does still include the Python capability, but as I say, it's augmented by these automatic program generators, which turns the test generation into a push button exercise. It also includes things like a automatic test sequencer. So in production environments, you can set up a predefined set of tests and run through them and record the results in an HTML format, or export the results as well. So it's a more sort of fully fledged test development and test execution platform. Okay, so I think we're now ready to wrap up the session. So thanks very much for joining us. Feel free to mail me any further questions you have, james@jtag.co.uk. And I think we've got another presentation coming on in a little while. So thanks for everybody that watched, and I hope to hear from you again. Bye for now.